So today's topic I'm going to discuss is modeling of registers and counters using Verilog. So to give a brief introduction or a few insights about Verilog, it's a hardware description language which is used to develop or model electronic circuits. Okay. So what we mean by modeling in these electronic circuits is we simply develop or design or model a few electronic circuits such as simple and gates to registers and even more complicated or complex structures of electronic circuits with a few simple lines of code. So it's simply a design method or a software which you can use to model or design electronic circuits, much bigger electronic circuits. And apart from that, the one more reason we use these hardware description languages such as VHDL or Verilog is because we can uh, design them digitally and we can transfer them. Apart from pen and paper writing, it's traditional method. So this is the modern or old modern or technical method of modeling system. So that is Verilog, and there are three types of modeling we commonly use. And the first one is data flow modeling. So if you know how data flows in and out of a system or an electronic circuit block, say an AND gate, OR gate, NOR gate, adder, half adder, full adder. So in all these cases, we know how the output will be for given values of input. So we know how the data flows, right? So if you say for a if the value of one input, both inputs of an AND gate is 0, then the output is 1. Sorry, the output is 0. And for if when the both inputs are 1, the output is 1. So we know that how the outputs and input change. We know the relationship between input and output. That is what how I use this data flow modeling. And one benefit of data flow modeling is we don't need to know how a circuit behaves. We just need to know how or what the inputs and what the outputs are. So based on that, we know how a circuit will behave. I mean, how the output will be. So we just develop a circuit just based on the fact that the inputs and outputs are known. So that is data flow modeling. Now, when we speak about behavioral modeling, so it's when we know how a circuit behaves. We just even if the in cases when the output is unpredictable or we can be sure of the output necessarily. So or it is complicated. Like we cannot predict, say, in the case of a full header, there are three inputs, and we need to know the outputs for eight combinations. Output for eight combinations of inputs. We need to know these two inputs for eight combinations of input. So that is a full adder. So what if it had eight, six, or seven inputs and three, four input outputs? So it would be more and more complex. So in that cases, we can use this behavioral model just by writing the expression by calculating or using simple K-map, QMA cluster or simple methods to simplify the expression, and we could write this behavioral expression, and this using this expression we could model a circuit block. Then the third one and the last one is structural modeling. So as mentioned earlier, so we know that a half adder or a full adder is a mix of a few logic gates. So we cannot, or it is harder for us to implement each logic gate or define each logic gate as a block separately throughout the program or throughout the design. So we use the structural modeling. So with the modeling of structure, with the structural modeling, what we do is we create modules and break down the entire design or entire program into smaller modules, and we assign structures. So we when we know the our working of a full adder, we just define it as a full adder module, and mm, and we can we can do much more functions we can focus on much more functions because we don't need to bother about how a full adder works and all. So that is structural modeling. So when you are focusing on bigger modeling and circuits, or bigger, say, sequential, or when you're working with a lot of registers and all, we would use structural modeling. So that is about a brief introduction of Verilog and all types of modeling. So now let's look at how we model. So the first topic is a cyclic shift register. So if you don't know how a say a register or a counter works, so this is how it works. So a counter or a sequential circuit, as you know, a counter is a sequential circuit. So it has a feedback, a part of output is fed back to the input. So that is one thing or one point which makes a circuit sequential. And the next part is it needs a triggering pulse or a signal to enable it. So in this case, it's a clock. And as you can see in this program, we have using the positive edge trigger clock. So which means the for the positive values or the high values, when the clock pulse goes from 0 to 1, the clock the our flip flops are triggered and they are turned on. And for the our flip flops only are on when the clock pulse is 1. So which means that for any other values, the flip flops will remain in the same state, and when the clock pulse returns to the same state, it will 1 minute. So 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 when the clock pulse, based on the clock pulse, the flip flops work. So when a clock pulse or clock signal is absent, all the flip flops will be turned off. So when the clock pulse is given, all the flip flops will be on. So what we are looking at is a cyclic shift register. So when a clock is given, so what is here, how it works is, here the input, as you can see, the D or the input to the first flip flop is given from the last input, right? So how this works is it keeps on counting in a different pattern. Like, say, the clock pulse is 1, the signal is it's from the last signal's output. Say the output of the last flip flop is 1, then this Q1 will be 1, and it will be put to the D flip flop, and this output will be 1 as well, and this output will be 1. So what happens here is the data in these three registers appears same. So for a different clock pulse, say, that is the reason why we use a clock pulse. So for a clock pulse, the next clock pulse, when this is 0, this clock is 0, this first flip flop will be turned off. So Q1 will be 0, and the next input D, when it is 0, Q2 will be 0. And so what happens is we turn on and off these flip flops. So this is how a hardware works. So the hardware version of our flip flop works. At the rising edge of clock, all of the inputs are rolled to flip flops, but the stage does not occur until after propagation delay. So this is the program. We use an always statement. Always statement, as you know, it's kind of like a while statement. Okay, so the difference from while is that it's okay. It's actually similar to while. So here in always set. So here the condition is at positive. We can read it from right to left for a simpler understanding. So it goes like this: at positive edge clock. Okay, when the clock is positive edge, always repeat these statements. Begin, from begin to end. So it's like a brackets in C. So begin these statements from begin to I mean execute these statements from begin to end when or always when the clock is positive edge. Okay, so what happens here is, say here Q1. The order of, so here in this case the order is not important. Okay, so it's not important. The program is just to show a non-blocking assignment operator. So a less than and equal symbol is used as the non-blocking assignment operator. The same result is obtained even when if the statements are in reverse order as shown here. So as you can see, yeah, the order is reversed. So it will be executed in any order. And you can see when Q1 less than or equal to 5. Q1 equal to Q3. Yeah. So yeah. Okay, okay. So what it means here is, so when Q1 is equal to Q3, so what here happens is, so for the output of first flip flop Q1, the there should be an input to the D, or the first flip flop's input D. So let's say D1, D2, D3 for these three flip flops to better understanding. So the output Q3 from this third flip flop is fed to our first flip flop's input. So what happens here is, so Q1 is equal to Q3, which means this the output of the first flip flop is equal to the third flip flop's output as well. See, the Q3 is fed back to the D, first input D1, and we get Q1. If D1 is equal to 1, or that is Q3 is equal to 1, we get Q1 is equal to 1. If Q3 is equal to 0, D1 is equal to 0, and Q1 is equal to 0. So Q1 is equal to Q3, Q2 is equal to Q1. That is Q2 depends on the Q1, first flip flop's output Q1. When Q1 is 1, D2 is 1, and Q2 is 1. Similarly, so we can say it simply by Q2 equals Q1 and Q3 equals Q2. See, so what we use here is a data flow model kind of. We use this always block to model data flow model, and this is a cyclic shift register. This figure 2.39, it's a cyclic shift register, and we are using a non-blocking assignment operator. So that is about it. So if you know what a cyclic shift register is, if you don't know what a cyclic shift register is, a cyclic shift register is a kind of register which um, transfers value. Like say we got a few values like 000. So if here there is one, from Q1 there is one, it passed to Q2, and here it becomes 0. Then Q2 becomes 1, Q3 becomes 0. It's simply like A1 getting passed from Q1, Q2, Q3. When Q3 is 1, at that moment, these two inputs will be 0. Q1 and Q2 will be 0. Then it is passed again. So Q1 will become 1, Q2, Q3 0. Q2 will become 1, Q1, Q3 0. So that is how it's goes. It's like a cycle of 1 getting passed from Q1 to Q3, and the process gets repeated. So name comes cyclic shift register. So next, so here is an example question. So here the question is, what is the hardware obtained if the following code is synthesized? So let's look at the code. So here we are defining a module reg3. So we are declaring or say we are initializing or declaring a module of name. Okay, so module just means functions, means C programming and all, which is just like functions. When we declare functions, we give them a name. So here the name of this module. Okay, module and functions are similar. So the name of this module is reg3. So it's a reg is component used for registers. So this is a register 3. Okay. So as we also know, should note that earlier when we used a cyclic shift register, we were speaking of 3 flip-flops. And as you know, a flip-flop or a D flip-flop is a register which can store 1 bit at a time. So a flip-flop is nothing but a register. Okay. So here the name reg3 because we are using 3 registers, 3 flip-flops to use 3 bits, to store 3 bits. So that's why we name reg3 and we declare this module reg3 and this bracket. Okay, so this bracket represents the arguments or the arguments in this function, or what are the variables we are going to use in this function. So what we are using in this function is q1, q2, q3, a and q2. So we just initialized or declare these are the variables we are going to use in this function. Okay, so that's what is. So uh, so this bracket is used for initializing or declaring this variable q1, q2, q3, a and clock clk. So here, as you notice, the input, there are two inputs a and clk. So as you are aware of, or if you are not, if you are aware of the inputs, the inputs in our case are b, which is the first input, and the clock clk, right? So these two are inputs and Q1, Q2, Q3 are outputs. So similarly, in this program, we are declaring input A as input. So instead of D, we are using A as input and input clock is another input and outputs are Q1, Q2, Q3. And we are also declaring them as registers because they need to store only a 1 bit. So either 0 or 1. So that's why we are declaring them as registers. So that is why we declare reg1, reg q1, q2, q3 because the three of them q1, q2, q3 are registers. These outputs are registers. Which means these outputs can only have positive values 0 or 1. So the outputs will be either 0 or 1. The values of q1, q2, q3 will either be 0 or 1. So that's the declaration part and the function declaration. So next we start at the always. So always at positive pos edge. So what pos edge means is at positive edge clock. So when clock is at positive, so what a positive edge means is, so we are aware of a square wave, right? Or a square pulse. So how does it appear? It goes from 0 to 1 and it remains 1 for a time period, then it goes to 0 and it remains 0 for a few time, sometime, then it goes to 1. So if you notice, you can uh, divide those ones and zeros as a sides of square, right, and edges of a square. So there are four edges. One edge when the clock is 1, it's stable, and another edge when the clock is 0, it is also stable. Then there are two edges, one rising edge and one falling edge, or a positive edge or a negative edge. So in a positive edge, the signal or the value goes from 0 to 1, so it's positive. So in a negative edge, the value goes from 1 to 0, it is falling. So it's a falling edge or a negative edge. So that is a positive edge and negative edge. So always at a positive edge clock begin and end. So what happens here is, as I mentioned earlier, whatever in this begin and end, it's like brackets. We use brackets in C programming and all. So it's kind of a bracket. Consider, or to get an easier understanding, consider these two begin and end as brackets. So what happens here is, always at a positive edge clock, execute these statements in between the and. So here the statements are Q3 is equal to Q2. So as you have noticed, Q3 is equal to Q2. So the value of Q3, the output of the third flip-flop, is Q2, the output of second flip-flop, and Q2 is equal to Q1. So the output of second flip-flop is equal to the value of first flip, output of first flip-flop. So and Q1 is equal to A. So Q1, the output of first flip-flop, is A, or say it's a modified circuit. It has an input A. Okay, so it's an extra input. Oh, sorry, it was my mistake. So here we have an extra input A, like an enable pin, something like enable pin, or to start this process or to alter this process. So based on this input, we can change the working of the slightly shift register. So what do you think has occurred here? So and after these three statements, it ends and end module. End module means it's end of function. We have declared this function. Here is the declaring of variables. Here what we have declared what this function does. Okay. Now we can just call this module register 3 anywhere in the program or code. So that's how this works. So answer is a 3-bit shift register. The hardware obtained from this following when this following code is synthesized. So a 3-bit shift register. So here the statements execute in top to bottom order. It's a general order of execution, but the order doesn't matter. In some cases it does, but in our case, this case, the last case we mentioned, the order does matter, but the case we mentioned before that, the order does not seem to matter, right? So like we didn't have an additional input, so the order didn't matter. Now here the blocking operator is used, which means the equal to sign is the blocking operator, and as we have learned about operators in other programming languages. In this Verilog, there are two operators like blocking and non-blocking operators. So this equal to sign is a blocking operator, and this less than or equal to sign operator, it's a non-blocking operator or a non-blocking assigned operator. And this is a block, and is equal to some blocking of assignment operator. Now, so the synthesis results in a 3-bit shift register with serial input A and outputs Q1, Q2, Q3. So while the register can be modeled using blocking operator that is equal to sign, but as an example, it is generally advised not to do so. As mentioned previously, in the earlier example, we used this non-blocking operator, that is the less than or equal to sign, and it is a good coding practice to use this non-blocking assigned operators while while writing synthesizable code. So it's a general coding practice or a good coding practice, and to use them in always block. Okay, so in always blocks, in that is in always blocks, it's a good practice to use these non-blocking operators, assigned operators. So if you want to understand non-blocking and blocking operators more detail, so what they are often used in these always blocks, and these non-blocking and blocking assigned operators are used to create combinational and sequential circuits. So we use a non-blocking assignment operator, that is this less than or equal to create sequential circuits, and this equal to blocking operator to create combination circuits. So what happens is when a blocking operator is used for assigning in an always block when a blocking operator equal to is used to assign values or to assign, okay, so simply assign. So what happens is the line of code, say, I will show you with an example. So here Q2 is equal to Q1 in this case, right? So what happens is this Q2 is equal to Q1, this statement 2 will only be executed if when this Q3 or the first statement is after the execution of first statement will only be this second statement executed. So similarly, this third statement also will be executed only after the execution of fourth statement, right? Oh, sorry, only after the execution of first and second statements. So one will be executed because it is the first statement. Two will be executed because of two will be statement two will be executed after the execution of statement one, and statement three will be executed after the execution of statement two and one. So that is the order in this blocking assigned operator. And in case of non-blocking assigned operators, there is no specific order. So say this Q2, this statement 2, Q2 is equal to Q2 less than or equal to Q1, could be executed before executing Q1. And Q3, this Q3 is equal to Q2 could also be executed before the operation of Q1 and Q2, or the first and second statements. So that is the main difference between Q1 and blocking and non-blocking operators. So just remember this fact. Blocking operators are used for developing combinational logic, and non-blocking operators are used for developing sequential logic or sequential circuits. So that is this. And now, so that is here we have a second example. So what is the hardware obtained if the following code is entered? Note that this is the same code as in the previous one, but the statement order is inside the always go reversed. Okay. So this is a good example. So what happens is here in our first example, we used equal to operator in a correct manner so that we could get a 3-bit shift register. In a perfect manner that we could get a 3-bit shift register. So this blocking operator didn't play any much role, and we couldn't see why this operator is why this operator should not be used in a sequential circuit. But let me show you in this example when this blocking operator is used and when the statements are reversed, uh, it will not result in a shift register because we cannot use a always block like this with also using blocking operators because the output will lead to only a single flip flop, right? So say Q1 is equal to A. So what happens is when Q1 is equal to A, so A is not defined, right? A is not defined. The value of A is not defined. So Q1 is A. Q1 is equal to A. So for input A, we get Q1 and Q2 is equal to Q1. Q3 is equal to Q2. So what happens is when a when this Q1 will be executed first because Q1 and Q2 will not be executed. Only the value of Q1 and Q1 will be executed. So if there is no Q no input signal A, there won't be a Q1, right? So it's like a let me show you. So the list of statements executed from top to bottom in order. Note that the blocking operator is used. So the first statement finishes update before the second statement. So as I said, The first statement, that is this one, q1 is equal to a, it should be executed first before statement 2 and 3 because we are using this blocking operator, right? So when the first statement is applied, so yeah, so q1 gets the value of serial input a. So and when the statement the second, yeah. So what happens here is when this a or this input as given, modern flip-flops, which is this modern synthesizing tools, they what they give as output is when this input A is given to this kind of an assignment or this kind of an assignment or in this always block for this kind of program, what happens is for when the serial the input A is 1, Q1 is equal to 1, and when Q1 is equal to 1, Q2 is equal to 1, Q2 is equal to Q1, and what happens is modern synthesized blocks will give you modern synthesizers will give you a single flip flop as an output. But the if the if the synthesizer does not reach or have good optimized algorithms, it will generate most probably generate three parallel flip flops at the same time, and each with same input A, but with outputs Q1, Q2, Q3 respectively. As mentioned, in example one, it's not a good practice to use blocking operator in always block intended to create sequential logic. So try not to use equal to operator in creating sequential blocks, and also try not to uh, include or use non-blocking assignment that operator that is less than or equal to in comprehensive circuit box. So that's a good coding practice to be remembered. Now, so as a summary, what we discussed the modeling of counters. So we discussed how a counter could be modeled. In by this, what we discussed was the shift register, but the counters have the similar way of implementation. Discussed the use of blocking and non-blocking operators. Discussed always statements, how always statements are used and how it works, and the use of non-blocking and blocking operators, where blocking operators should be used and where non-blocking operators should be used. So that's the my topic. So that's my topic for today, modeling of counters and registers. And I hope you understand and learn. Please ask me if you have any doubts and clarification so that I could make it more understandable to you. Thank you.